In 2015, there was huge excitement in the space community. That is because, up until then, the best image available of the Pluto system was a blurry representation. Hubble had also observed Pluto, but due to its small size and immense distance, the best it could capture were a few blobs of color variation. However, in 2015, this all changed. After a 9-year journey, the New Horizons space probe flew by the dwarf planet, providing unprecedented detail and fidelity of Pluto and its moons. This raised the question, what did the New Horizons probe see and discover during its flyby of the Pluto system? And what has it been doing since the flyby? This narrative will explore the highlights of the New Horizons mission to the Pluto system and beyond, offering a detailed look at the discoveries made and the significance of this mission. To provide context, Pluto is a remarkably small and distant world, much smaller than Earth's moon. It resides in the Kuiper Belt, a dispersed region of asteroid-like or comet-like objects beyond Neptune's orbit. Pluto was the last of the traditional 9 planets to be explored, primarily due to its distance and the perception that it was not a particularly interesting celestial object. Fortunately, the team behind the New Horizons mission advocated strongly for its approval, and in 2006, the probe was launched as part of NASA's New Frontiers program, which focuses on medium-budget space missions. The mission's goal was to reach Pluto as quickly as possible, and New Horizons was the fastest spacecraft ever launched at the time. It was a lightweight spacecraft carried by the most powerful rocket available, a fully boosted Atlas V. The probe passed the Moon in just 9 hours, a feat that took the Apollo missions 10 times longer. On its journey to Pluto, New Horizons used Jupiter for a gravity assist, which reduced its travel time by 3 years. It also tested its systems by capturing remarkable images and videos of Jupiter and its moons. After this successful trial, the spacecraft entered hibernation mode to preserve its instruments. As it approached Pluto in 2015, the team reactivated its systems, and daily images of the Pluto system were transmitted back to Earth. This was an exhilarating time for space enthusiasts, as the resolution of the images improved daily, revealing more details about Pluto and its largest moon, Charon. Among the most striking features was a heart-shaped formation on Pluto's surface. On July 14, 2015, New Horizons made its closest approach, coming within 12,500 kilometers of Pluto's surface. However, mission controllers did not receive the data immediately, as the probe was occupied with capturing images during the flyby. Once data transmission began, the slow uplink speed of 1 kilobit per second and the 4.5-hour latency between the spacecraft and Earth posed challenges. Nevertheless, the images and data sent back were spectacular, revealing mountain ranges, ice plains, glaciers, and an atmosphere. The mission also provided detailed observations of Pluto's moons. One of the first discoveries was the unusual relationship between Pluto and its largest moon, Charon. Charon orbits very close to Pluto and is relatively large in comparison, causing the barycenter, or center of mass, of the two objects to lie outside Pluto. This means they both orbit a point in space. Additionally, both Pluto and Charon are tidally locked to each other, meaning the same side of each object always faces the other. This is rare, as while some moons are tidally locked to their parent planets, the reverse is not typically true. Charon's darker appearance suggests it has a different origin than Pluto. The other moons of Pluto are much smaller, only a few kilometers across, with circular orbits aligned with Pluto's orbit. Pluto's geology is fascinating, with its most prominent feature being the heart-shaped Sputnik Planitia, a vast ice plain the size of Texas. This region, composed primarily of nitrogen ice, has a strong color contrast with its surroundings. The surface temperature on Pluto averages negative 229 degrees Celsius, causing water ice to be rigid and brittle, while nitrogen ice behaves like water ice on Earth, flowing as glaciers. These glaciers are visible around the edges of Sputnik Planitia, filling gaps between craters and mountain ranges. The ice plains are marked by giant polygonal shapes, likely formed by sublimation, where ice turns directly into gas. The lack of craters suggests the surface is relatively young, possibly only 10 million years old. Sputnik Planitia may have formed from an impact, with ices filling the crater from a potential subsurface ocean. This basin creates a positive gravitational anomaly where gravity is stronger than elsewhere on Pluto. The ice plain faces away from Charon, aligning with the tidal axis between the two objects. The strong tidal effects likely contribute to Pluto being tidally locked to Charon. Surrounding Sputnik Planitia are mountain ranges made of water ice, the only type of ice strong enough to support such heights at Pluto's temperatures. Among these mountains, some may be cryovolcanoes, such as Wright Mons, which stands 4 kilometers tall and features a central depression. Cryovolcanoes could play a role in renewing Pluto's surface. Another intriguing region is Tartarus Dorsa, characterized by 500-meter-high mountains resembling snakeskin or tree bark. These formations are thought to be penitents, a rare feature also found on Earth in high-altitude, dry regions like the Atacama Desert. On Pluto, they are much larger and cover a vast area. Pluto's surface also features dark material, particularly in a region called Cthulhu Macula, which resembles a whale in shape. This area is heavily cratered, indicating an older surface compared to Sputnik Planitia. The dark color is likely due to tholins, a tar-like substance formed from hydrocarbons interacting with sunlight. Similar deposits are found on Saturn's moon Iapetus. The distribution of tholins on Pluto is uneven, raising questions about the processes behind their formation and whether Pluto's surface is dynamic or stable over time. Tholins may be linked to cryovolcanism, as water and tholin mixtures have been observed erupting from cryovolcanoes like those in Viking Terra and Virgil Fossae. These eruptions create varied landscapes, with slurry flowing into craters and troughs. Hubble data suggested Pluto was becoming redder, and New Horizons may have captured Pluto during its reddest phase. The most intriguing findings about tholins, however, are not on Pluto, but on its twin dwarf planet, Charon. In this enhanced color image of Charon, the most striking feature is the red cap over its north pole. Remarkably, due to Pluto's weak gravity, some of the slurry mixture ejected during cryovolcanic eruptions escapes Pluto entirely and travels the 19,000 kilometers to Charon. The tholins, a tar-like substance formed from hydrocarbons, are concentrated in this region because Pluto and Charon are tidally locked to each other, always showing the same face to one another. Poetically, this means Pluto perpetually hides its heart-shaped Sputnik Planitia from Charon in their eternal dance. As a result, tholins accumulate in a specific area on Charon rather than being distributed evenly across its surface. Charon itself has also yielded fascinating discoveries. Unlike Pluto, whose surface is dominated by nitrogen ice, Charon is primarily a water ice world. This difference means Charon lacks a significant atmosphere, as its water ice remains locked to the surface. In contrast, Pluto's nitrogen ice sublimates and refreezes with the changing seasons, causing its atmospheric density to vary dramatically over the course of its 248-year orbit. This seasonal cycle can alter Pluto's appearance significantly. One of the most impressive findings from the New Horizons mission was the confirmation of Pluto's atmosphere. The images captured are extraordinary, showing the atmosphere extending high above Pluto's surface due to the dwarf planet's small size and weak gravity. Earth's atmosphere, by comparison, hugs the planet tightly because of its stronger gravity. Pluto's atmospheric pressure is exceptionally low, around 10 microbars or 100,000 to 1 million times weaker than Earth's surface pressure. However, it is theorized that the pressure could increase to as much as 18 to 280 millibars at certain points in Pluto's orbit, when it is closer to the Sun than Neptune. This increase would cause surface ices to sublimate into gases, a process evident in Pluto's ice plains. The last time Pluto's atmospheric density was thought to be similar to Mars's was 900,000 years ago. Under such conditions, liquid nitrogen could potentially form on Pluto's surface, and there is evidence of what appears to be a frozen lake. Within a single year, Pluto's atmospheric density can vary by a factor of 4 due to seasonal changes, a stark contrast to other solar system objects with atmospheres, which generally remain stable. Pluto's atmosphere consists of the same ices found on its surface: nitrogen, methane, and carbon monoxide. Another intriguing discovery is the presence of up to 20 haze layers in the atmosphere. While haze layers were expected, their abundance was surprising. These layers, visible in some images, resemble thin fog, with sunlight streaming through them and casting shadows from Pluto's mountains. The layers are not uniformly distributed. In some areas, they touch the surface, while in others, they float high above. These images, showcasing the depth and scale of Pluto's mountain ranges, are particularly breathtaking. The mountains appear strikingly tall because Pluto's gravity is too weak to pull them down, giving the dwarf planet a toy-like appearance. In June 2020, scientists published a paper suggesting that Pluto may harbor a subsurface ocean of liquid water, similar to the icy moons of gas giants. This finding challenges the earlier assumption that Pluto formed cold due to its distance from the Sun. Instead, evidence from New Horizons indicates that Pluto had a hot start, meaning it may have always had an ocean. If true, this raises the possibility that Pluto could be as habitable as some of the icy moons closer to the Sun. Furthermore, if Pluto is representative of other dwarf planets in the Kuiper Belt, there may be numerous habitable worlds in this distant region. The evidence for a hot start includes surface features indicating expansion rather than contraction, such as cracks showing the crust moving apart. This suggests that Pluto may have been an ocean world shortly after its formation, heated by bombardments from planetesimals during the early stages of the solar system. This discovery offers a new perspective on the formation of the solar system. While the absence of craters is most notable in Sputnik Planitia, the general scarcity of craters on Pluto and Charon suggests that the Kuiper Belt may contain fewer small objects than previously thought. The New Horizons flyby of Pluto lasted only a few days, after which the spacecraft continued its journey into the Kuiper Belt. By this point, New Horizons had traveled so far from Earth that it observed the Alpha Centauri star system from a significantly different perspective due to the parallax effect. This shift in perspective highlights the vast distances New Horizons has traversed. Despite its incredible journey, the spacecraft's view of Alpha Centauri is the only noticeable change, underscoring the immense scale of space. After the Pluto flyby, New Horizons remained on a trajectory deeper into the Kuiper Belt, a largely unexplored region. The mission team had identified a new target for the spacecraft, Arrokoth, an object discovered after New Horizons was launched. In the year preceding the Pluto flyby, the team used the Hubble Space Telescope to locate potential targets and identified 3 new objects. Arrokoth, a 35-kilometer-long object, was chosen for its proximity to New Horizons' path. This made Arrokoth the first object visited by a spacecraft that was discovered after the spacecraft's launch. New Horizons, still in good condition, with remaining fuel and power from its radioisotope thermoelectric generator RTG, was directed to adjust its course for a rendezvous with Arrokoth. Little was known about Arrokoth initially, as Hubble could only detect its color and brightness variations as it rotated. However, scientists used an occultation event where Arrokoth passed in front of a star to predict its shape. This prediction proved remarkably accurate, revealing Arrokoth to be an elongated object, possibly a contact binary or a long asteroid-like body. In August 2018, 3 years after leaving Pluto, New Horizons began its approach to Arrokoth from a distance of 172 million kilometers. At this range, Arrokoth was barely visible against the backdrop of stars. By December 2018, however, it became clearly visible to New Horizons as the spacecraft closed in at 51,000 kilometers per hour. As New Horizons approached, Arrokoth's bizarre shape began to resolve, confirming it as a contact binary, a unique and fascinating object unlike anything previously observed. Arrokoth, the distant Kuiper Belt object visited by New Horizons, is relatively crater-free and has a lumpy surface, making it unlike any asteroid or comet observed up close before. On January 1st, 2019, New Horizons made its closest approach to Arrokoth, coming within 3,500 kilometers of its surface. During this flyby, the spacecraft captured the majority of its scientific data, making Arrokoth the most distant object ever visited by a spacecraft, located approximately 6.5 billion kilometers from the Sun, about 45 times farther than Earth. Due to this immense distance, the data transfer speed between New Horizons and Earth was extremely slow, at just 1 kilobit per second. Despite this limitation, the fact that communication was possible at all is a testament to the advanced technology involved. The slow transfer rate meant it took around 2 years to send all the data collected during the flyby back to Earth. The highest priority data, including images, was transmitted first, though the highest resolution images took longer to arrive. As a result, when media outlets initially reported on the flyby, only low-resolution images were available, meaning much of the public never saw Arrokoth in its full detail. Now the highest resolution images reveal Arrokoth in true color, showcasing its reddish hue, which contrasts with the darker, grayer appearance of most asteroids closer to Earth. This red coloration is due to the presence of tholins, organic compounds formed when solar and cosmic rays break down substances like methane and ammonia. While Arrokoth no longer contains these volatile compounds, likely due to its low mass, its surface spectra reveal the presence of methanol, hydrogen cyanide, and water ice. The abundance of methanol, which becomes red when irradiated, is the primary cause of Arrokoth's color. However, a mystery remains in Arrokoth's spectra, an unidentified absorption band at 1.8 micrometers, representing a compound not yet recognized by scientists. Without a surface sample, this compound remains a puzzle. Another striking feature of Arrokoth is the absence of small impact craters, which is believed to reflect the nature of the Kuiper belt. While the Kuiper belt may contain 20 to 200 times the mass of the asteroid belt, much of this mass is concentrated in large bodies like Pluto, and the region is far more spread out due to its vast size. The slower orbital speeds in the Kuiper belt mean that any impacts occur at much lower velocities compared to those in the inner solar system. For example, meteorites entering Earth's atmosphere can reach speeds of 75 kilometers per second, while impacts in the Kuiper belt may occur at just 300 meters per second. This low-velocity environment means that what appears to be a crater on Arrokoth might instead be a sinkhole caused by the escape of volatile substances beneath the surface. The lack of significant collisions suggests that Arrokoth is a pristine time capsule from the early solar system, preserved for billions of years. Its unique shape, consisting of two lobes, may have formed through a slow collision or from two bodies coalescing in a swirling cloud of ice fragments. If the lobes formed side by side, they could have gradually merged at speeds no greater than 2 meters per second, with both objects tidally locked to each other before joining. The similarity in appearance between the two lobes supports the theory that they originated in the same region. Originally nicknamed Ultima Thule, Arrokoth's individual lobes are now known as Ultima and Thule. Bright regions on its surface, particularly in the crater-like depression and around the connecting point between the lobes, are likely caused by avalanches or the accumulation of volatile substances like ammonia ice. The bright patch at the connecting point may also result from loose material rolling down the lobes and collecting at the center due to gravity. With a low density of 0.5 grams per cubic centimeter, Arrokoth is likely porous, and volatile materials escaping from its interior over time would have frozen on the surface, leaving behind a rocky core. New Horizons also detected that Arrokoth is slightly warmer than expected, at 29 Kelvin instead of the predicted 12 to 14 Kelvin, suggesting some internal heat source. One of the most surprising discoveries about Arrokoth, revealed only after detailed analysis of New Horizons data, is that it is much flatter than anticipated. This flatness was not immediately apparent because Arrokoth's rotation limited the angles from which it could be observed. The cause of this flatness remains unknown, but possibilities include centrifugal forces during its formation when it may have spun faster than it does today, or the uneven exposure of its surface to sunlight over decades, causing volatiles to escape more from one side than the other. Research is ongoing to determine the exact cause. As New Horizons departed Arrokoth, it captured one final image of the object's silhouette against the stars. This may be the last close-up view of Arrokoth ever obtained, as it is uncertain whether another mission will visit it. Looking ahead, New Horizons still has power and 11 kilograms of fuel remaining, and efforts are underway to identify additional targets in the Kuiper belt. If no suitable objects are found, New Horizons will follow the path of the Voyager probes, passing through the heliosphere and into interstellar space in the 2030s. Even without another flyby, the mission team is proposing an extended mission to repurpose New Horizons as a unique observatory. Positioned in the Kuiper Belt and the outer heliosphere, New Horizons could conduct groundbreaking planetary science, astrophysics, and heliospheric observations. These studies could include new observations of Uranus, Neptune, and dwarf planets, searches for free-floating black holes, and investigations of the local interstellar medium. New Horizons has already provided invaluable data on Kuiper Belt objects, revealing unexpected details about Pluto, Charon, and Arrokoth. These discoveries highlight the diversity and complexity of the Kuiper Belt, suggesting that many more surprises await in this distant region of the solar system.